Okay, so on this talk, I'm going to try to compress 10 years of work within 1 hour, which is going to be a little tricky. So yeah, I'm going to explain how I do procedural geometry in my demo. So I don't do remarks myself. I just use polygon. So it's like different process. There's different problematics. And so I will try to explain what is my pipeline that I used for all the previous production and that I use for other things as well. So when I wanted to do procedural geometry, I had a bunch of things that I wanted. I had motivations and requirements. So like the first thing, I wanted to be able to stack a modifier. So basically, for example, you start with a sphere, and you apply one modifier, and then you apply another modifier. So you apply this type of chain of modifier, which is not something you can really do with remark. And so it's easy to add a new modifier, remove one, just control a specific one. So you have a lot of, well, you want kind of control. The second thing is I wanted to emit geometry, which is probably the most important, and which is what is very difficult to do with something like vertex shader, for example. Because when you do vertex shader, you only can modify the position of this vertex. But you can say, oh, I want a new vertex, or I want a new triangle. You can't do that. And that was a massive problem for me. So it, in a way, it became at some point possible with geometry shader, but it has a lot of limitations which are very annoying. So we'll speak about it later. The next one is I need to keep geometry indexing, which is also very important because I don't want, if you start to replicate vertices, you start to get a lot of memory because one vertex is like 12 bytes for position plus 12 bytes for normal. You add 8 bytes for UV, every attribute you add a lot of memory footprint, which is a massive issue. Whereas if you use indexed geometry, that means basically you just have ints. So if you emit 3 times, instead of emitting 3 times 36, you emit 3 times 4, which is a huge gain. And also keeping geometry indexing allows you things like recomputing normals, which is not possible. And so other thing, which is what I do all the time in my production, I start from very simple geometry and I make complex structures out of it. So for people who've seen Return, basically the whole city is a rectangle. And every frame, the rectangle becomes a city. But like I restart every frame with the rectangle and I rebuild the city from scratch every frame. Which is going for the next thing, which I want things fully dynamic. So I need to rebuild everything every frame because it needs to be dynamic. So if I change a parameter, it can change the whole structure. I want control over emitted geometry, but I'll go to that later. I want to avoid unnecessary geometry expansion because, for example, if you want to say, oh, I emit like 10 triangles every time, like every pass you will emit 10 triangles. So that means you will go 10, 100, 1,000, 10,000. So every time it's gonna expand a lot. And that means the more pass you have, you can go to really high. So I want to reduce the number to be able to do more modifier. I want to decouple displacement amount to modifiers that I will explain a bit later. And I want to easily create new displacement function or operators, so that's the same thing I really need to decouple, because the problem is, for example, if I say displace from this function or displace from this function, if I have like 10 types of modifier and I have 10 different functions, I don't want to have to rewrite the full code for like 1,000 shaders. I want to be able to, so well, it's basically code generation, kinda, to be able, I want to write a simple new function, and then I just plug it to this type of modifier, and it just works, hopefully. Not always, but. And I don't want to only use triangle, but I want to use quads, because a lot of modifiers are extremely easy to do with quadrilateral, but are extremely hard to do with triangle topology. So I want to be able to do that things like with not only triangle primitive, but quads. So Well, it went through a lot of iterations from like CPU-based bad vertex displacer, which were terrible. Then it moved to geometry shader, but as soon as we could, we moved to compute shader. So all our pipeline is based on compute. We always use a header with utility functions, so we can change our data structures quite decently. Otherwise, if you have like 20 shader and you change one part of data, I don't want to change 20 files, so I want to try to avoid this type of things. We used to use, well, I don't know if you, yes?
Can you set the slide to full screen? Like just presentation mode should do it. It should be on like,
oh, that's way, I think? Yeah, cool. No problem. So yeah, we used, for people who are familiar with DX11, we used the counter buffer, append buffer at the beginning, but we had a lot of limitations, so now we use purely byte address with atomic functions. Which sadly, yeah, was a bit more than a header change because it was much more complicated. So why don't we use structured buffers anymore? It did a good job for a long time, I mean, but it has problems. So it's very easy to use. It's more or less a GPU array. So it's like you manipulate an array in GPU or in CPU. Obviously, you have parallelism to take into account, but code-wise, it's reasonably similar. Append and counter buffer are really reliable. It's easy to change to indirect because all our counters are managed in GPU, so we have to deal with a lot of this indirect dispatch and draw in compute. But in the case of append counter, you use copy structure count and you just change a small buffer. It's not that bad. So now the problem with structured buffer, at least in DX11, because we still use DX11, is you can't use a structured buffer as vertex buffer at the same time, and you can't use a structured buffer as an index buffer at the same time. That's not allowed, which is completely stupid, but that's the way it is. In DX12, it's possible, so that would mean that would make a difference. So vertex part is very easy to solve because you use vertex ID in your vertex shader and you just fetch. So instead of pushing a vertex, you just pull it from the index. That's very straightforward. You still need to make specific vertex shader to do the pull instead of using the same that you use for your standard pipeline. Index part is more problematic because you don't have access to it. It's reasonably okay. You can do a quick GPU copy to a byte address. But yeah, it's still annoying to have extra memory copy for nothing. And structured buffer has a really weird thing, especially on ATI. It's like an opaque data structure, so you don't know the memory layout. That's why in DX11 it's difficult. You can't bind it as vertex and index. So it's kinda, you don't really have control about what you do. And the last problem is, for example, append and counter only work with single increments. So append, you say, push me a new triangle. Counter, you say, push me a new vertex. So if you want to push 3 vertices, you have to say, call increment counter 3 times. If you want to push like 5 triangle, you have to call append 5 times. And that means you have no memory locality because everything runs in parallel. So that means if you say, push me 5 vertices, you don't know if they're going to be in order. And that also creates a lot of issues. But it did a good job for a while, but now we finally moved to byte address and interlocked, so atomics. So it's much more verbose to use, because you need to load address, you need to use as uint, as float to do the casting. But it has a lot of advantages, so you have full freedom on data structure. You can do pretty much whatever. It's just an array of stuff. So you could say it's a void pointer, if you want to call it that way, and you just put whatever you want inside. It doesn't matter. So we still made some utilities on headers to just say like load position, store position, because we don't want to do this conversion everywhere. I will show some code on example later, of course. And now, the good thing with the byte address, it can be used directly as vertex and index buffers, so it integrates much more easily in the pipeline. and it can still be attached to vertex or the stage. So that means we can attach it as push and pull at the same time, which is quite interesting. So that means we can push this vertex, but we can still access the neighbors, for example. So we can do both at the same time, which is actually really powerful. We don't need copy structure count anymore, which is not complete horrible, but it's still a bit better. And it also means now we can allocate indices instead of pushing one by one. So for example, if I have a modifier which emits 5 triangles, I just say I need 5 triangles now. And that is a massive difference because now I know this 5 triangle will be local in memory. And next, we had issue with counter buffer because we had to reset to 0 and make a lot of weird things not needed anymore. Huge issue with byte address and atomics. It's extremely unforgiving, and especially on NVIDIA. So we had a lot of issue with a lot of, I don't want to even think about it. It's definitely very complicated. It's been fixed reasonably well lately, but for some years it was really horrible. And yeah, this model is much less forgiving than the previous one. So append was, you could do mistakes and it was okay. With byte address and interlog, the smallest mistake, you'll have like flickering everywhere, you don't know. And so yeah, I would say if you don't have shader hot reload, so if you can't recompile shader on the fly, don't do byte address, basically. Structured buffer, it's okay, you can have decent control, but don't do it with byte address. So how does our structure work? It's actually reasonably straightforward. So we have a small buffer which contains all the data from our geometry. So we have vertex count, instance count, start vertex, start instance. So it's just the standard draw arguments. And we have the same with indices, instance, start index, base vertex, start instance. So it's the draw indexed argument. So if we want to draw per vertex, we can use the location of the buffer. And we have tx, ty, tz for compute to apply this thing for the vertices. So we have some modifier which work per vertex. We have some modifier which work per triangle. So then we have tx, ty, tz for indices. We have face count, which is just indices divided by 3 for triangle or divided by 4 for quads. We have last pass, vertex, index, and face, which is a number of emitted primitive on last modifier. So that means we can get the next modifier to say, for example, only process the thing from the last pass, not for everything. So it just allows us this little extra control. And we have like tx, ty, tz for vertex, last pass only, so same thing. And same thing, we have like utilities to access data, and we have a 1-1 compute shader. So after each modifier, we have like one compute which will just like update this data. So it will say now this number of things have been emitted, so we do a quick recompute. Rest of data structure, so we have one buffer per attribute, so we don't compact everything together. It's bad, you should not do that. So it's like one buffer is for position, one buffer is for normal, and in my case, position and normal are mandatory, all the rest is optional. Vertex is read-write, you don't need ping-pong. So an optional attributes, we have UV, object center, object ID, color, center, weight, so we can have like a lot of different things. And modifier use define to control if we use read-only or write-only, which is also really important, because if you bind as read-write for read-only, you're going to lose a lot of performance. So you should always know if you're reading only or read-write. So it's very important. So you just... And for index buffer, we still need to ping-pong. That's, in that case, we have no choice. And if we have some extra attributes per, like for index, we need to replicate them as well. So in that case, it's okay. It's only 12 bytes of ping-pong. If you did it with vertex only, it will be like a huge, like it will be like 5 times the size. So it's pretty reasonable. And it's 16 for quad. So we don't have choice for that. And face also have attributes which are only in place for some displacement. And face also have a generation attribute, which is like, well, I will speak about it later. Okay, so now for vertex modifier, it would work reasonably similarly as a vertex pipeline. It's you just never modify vertex count, you just grab a vertex, you change the attribute, and you're done. So it's the same. It's like basically you do the same as you will do in the vertex shader, but you do it in compute. It has one big advantage though. It's like because now when if you do shadow, for example, you will need to modify the vertex shader twice because you will need it once for the shadow pass and you will need one for the like gbuffer pass or forward pass, no matter what you use on your pipeline. Whereas if you do it in compute, you do it only once and then you just attach the thing twice. So you do only one pass of modifier. So it's perfect for read-write. You just take some attribute, compute some displacement amount, apply it, write same thing as you will do in vertex, but the big advantage is in compute you can reuse it. So if you have like 5 shadow maps, instead of changing the pipeline 5 times, you do it once in compute, you just draw it 4 times for the shadow in the exact same way, and you draw it like and you draw it once maybe differently for the gbuffer. So that's how it kind of works. It's pretty straightforward. So that's a displace function here, which is just do something from the position. So you have all the things like check how many vertices, make sure you don't overdraw, and just read your position, read your normal, compute your displace, and then, for example, here it's a displace along the normal. So if you want to say like apply some noise or apply a texture, you just change the function here. And from the function, you just have a displace amount which changes. So you can use texture, cube maps, whatever noise, sign, any function you want. And you just write the position back, that's it. So that's how it works. It's a bit like a vertex shader. The only, as I said, big advantage is you can do it only once. And so if you have like 5 lights with shadow, you do it once, which is much better. Well, in practice, in our case, it's a bit more complicated, obviously, because we have a bit more case. So we have this displace function, which says take the position and change. We have this operator, and we have a direction function. So displace compute say how much do you want to displace the geometry. Operator will say, like, we can add an extra function. So for example, you can say displace from a texture, but we want to say clump 0 to 1, and we don't want to write 20 functions like displace then clamp, so we separate it. So we have different set of functions for different purposes. And direction will say, for example, by default we displace along the normal, but we can say we want to displace along a certain axis or morph or different things. So that's how it works inside then. So we have the same as before. We say like that is our position, that's our normal displace. So all functions are optional. So if you don't inject the function, it takes a sensible default. So displace amount will say pick me the function of displace that I chose. Then it will say apply some little operator like clamp, absolute value, this type of gamma functions. And then it computes finally this extrude amount. And then we'll say this is a direction. So if we have no direction, we do normal. Oops. Otherwise, how do we do previous in that? So we can either use a custom function. By default, we use normal, and then we apply our extrusion. So face modifiers are much more complicated because like vertex modifiers, they just read-write, so they take a vertex, they change the position, but now this is when it becomes more interesting. Like face modifiers, they can A, emit new points, or B, emit new primitive, which is, so there's a couple of things. So we want the creation of the face to be conditional. because sometimes you want to say you want to emit new face in that case or not. It's really important, otherwise you're gonna have a huge model for nothing. So yeah, the simple default that we used before was to just emit primitive with a 0 display, so it's just like a flat triangle, for example, but obviously you still emit primitive. So that means you get really, it really grows exponentially. So like if you take one modifier that take one face and create tens, it's like 1,000, 10,000, and like after 5 passes, you're already at 1 million. And in our demo, we have something like 20 passes at least. So that means we would be at like nearly 1 billion polygon, which will not really work that well. So we need to do conditional emission. It's like, yeah, even just very low poly model will be like really huge. So for face modifier, like the displacement is exactly the same function set as vertex. So that's really cool for us because if I write, for example, a new displace function, I can use it either for vertex modifier or for any face modifier, which is really great. But we have 2 additional functions. The first one is predicate. So it will take this triangle and it will say, do you want to apply this modifier on the triangle or not? So it's like it's a condition function. So for example, we can say, if this triangle is too small, then just re-emit the triangle and don't do anything. So just push back the triangle, same as it was. So that is really useful. And the other one is point selector, which is a bit weird, but it's by default when you take the reference point for displacement, we take the triangle center. But point selector allows us to say, for example, take this edge, take the middle of the edge, take the center of the diagonal. So we can have a bit of extra control about that. And yeah, predicate is really the most important part to control the count. Like it really changes the amount of generated geometry. So for face modifier, now we use this allocate model. So that is when it becomes very difficult with atomics, because what we're gonna say is every modifier is responsible to say how many vertices and faces it wants to push, because we're not into append anymore. Like with append, we could say, for example, append 3 triangle, and if we have this condition, append another one. That's completely easy. But now we're not allowed to do that anymore because our NVIDIA card is gonna destroy us. So we have to say if this condition allocates 4 vertex, otherwise allocate 3, but we only allow to do the allocation once. Otherwise you're gonna go into nasty driver bugs. That's why I said it's very unforgiving. So, well, allocate vertices is pretty straightforward. You just say, we have our buffer location with our vertex count. We just say, I need 3 more vertex. And for face, I can say I need 5 more triangle. But you have to only call those functions once each. You're not allowed to call them more than one. So that's exactly that. And obviously now, like anything, if you overwrite, then it's up to you. Because if you, for example, say I allocate 5 vertex and you write 6, then, well, you're gonna have massive flickering because there's no bounce check, pipeline does nothing for you, you're gonna have no warning. So it's pretty unforgiving, but it's still pretty powerful. We still have a bunch of utilities to do fake append, but if we do one append too much, we get to flickering again. And so now the important part is, yeah, we want to be able to reuse functions because, let's say, I will make an example on live, that will be a bit easier. Okay, so shift O. Yeah. So I'll take shift. Should have one now, not. Draw normals here. apply, apply modifiers here, and yeah, I have background already. Just do a render texture, that will be fine. Okay, I will take just a basic sphere for the example, that will do. Okay, now we have, yeah, and I will put my preview here. Here, and I will just make them as flat. So that's the example. So now, for example, let's say I have like one modifier, which is like pyramid. Here, no, that's the wrong one. Oops. Pyramid, triangle. No, so I have my pyramid here, and let's say I want to do tube. Yeah, this one. So now if I say I want tube, I have tube. So it's different type of shapes depending on the modifier. But the thing is I want to use the same function set. Like if I want to say, for example, I want to displace with a noise function. So like let's say noise delay here. Okay, so now I have this noise delay, and let's change the timer here. Okay, so now I can apply it with a noise. But the thing is now, if I want to just reuse that, I have tons of functions. So like I say, displace like planar, which will take a texture. I just do wave here, and I'll use it on the pyramid, and hopefully it should work. Yes. Yeah, so now I'm just applying it on the texture, on the XY. So I have a lot of those displace functions, and I want to be able to compose that, because I want to be able, if I create a new shape, like for example, I have, let's say, a ring modifier, and I replace it. So now I have a new shape again, and I put that here. So yeah, I want to be able to compose things, because I don't want to rewrite all that things. Those shaders are actually quite complicated. So the idea is I want to be able to have a simple functions, and I want to be able to inject them. Because that also means if I want to write a new functions, I just say like write my whatever random formula, and I can reuse it on every displacer, which is quad, vertex, triangle. So it's like a massive benefit, of course. So yeah, in our case, like in our tooling, like shader, which accept functions, we don't call them shader, we call them host. So it's basically a shader which can get injected new things inside. That's so like, we also always want them to, if you don't inject a function, they should still work. So it's a host, but even if you don't provide anything, they should provide a proper default. Otherwise, like it will be a nightmare for debugging. And we use macros in our case for shader include to compose shader. So you could do code generation, but we found like include was better. It's more reliable, and well, it's just both versions are legit. You can use whichever you want, but I just found like code generation made debugging really complicated. It was. And yeah, include makes code much cleaner because, well, you just write your stuff. So yeah, so here we have like, so for example, if we have no displace function, we do that, and we have a custom include system. So when we call the compiler, we say, oh, if you have this function, just inject the code instead. So we don't have to do all this string manipulation, which can be very tedious, hard to debug. So like include used to work much better because we work at the compiler level. So if we do something a bit wrong, the compiler say, well, this is wrong here, done. So it's much, much easier for us. And next, yeah, the function composition. So every of those shader has, if it's enabled, call it. If not, use the default. So like you displace by one. If there's a function, you just replace. The great thing is the compiler will also remove dead code. So like if we have some, like for example, if we have this thing and we don't use it, the compiler will just get rid of it for us. So we can still add this extra code and make sure the thing is very clean, which is quite great. So yeah, that's just how it works. So when I connect, if I go back here, so when I basically connect this function to this host, it will say, oh, this function got connected to this host. It will go to the internal host compiler, which will say, oh, you need to enable this flag, and you need to inject this function code inside this shader. That means if I do that, I just recompile the shader behind the scene. If I do that, I did quite the same as well. So it allows us to have like tons of functions. So for example, if I take this here, and I will do, yeah, just back to, let's do an IQ noise. Oops, not this one. Yeah, so now if I replace by this here, and now I want to say, for example, absolute, and now it goes into absolute value, so it removes the negative. And now you can just like say animate, and well, do whatever you want with it. And so yeah, hosts, they use a custom handler. Also, we cache bytecode on the host, so that means when we do our demo at the end, like we have zero compiling. Like any of our production, we compile zero shader from the exe. Everything is already pre-compiled. It knows everything that needs to be done. So that means everything which is connected here, it knows exactly the parameters. It compiles bytecode. There's no compiling functions anywhere in our prods, which is quite nice also. Yeah, so that's, and now, yeah, the thing is, we want also to very easily create custom functions. And well, ideal workflow for us, which is something which we kind of achieved, not exactly, but not so far. So we want to write, for example, I want to write a new function. I don't want to do any C++ code or C# code or anything. I just want to write this quick XLSL function, like say, this is a displace amount I want to take from this function, and I want it to be immediately available as a block here. I don't want to have to write any of boilerplate and things. So it's not completely straightforward. So we use a bit of undocumented feature in FXC, which is called library compile. So the idea of library compile, I will actually, this option, window, system, open, application. If I take data shaders library, oops, no, XLSL, library, and for example, let's take some displace texture, that will do. I just, that's a bit suck. Let's do it like that. Yeah, okay. So the idea with library is you do something called export, and actually you can export this as bytecode. So it doesn't do anything, it's just bytecode of function. And you can, but the big advantage of it is you have actually access to reflection. So any function with export, you can just inspect the whole function on reflection. So you can, it will tell you the return value, it will tell you what parameters are in, what parameters are out. And that is actually really good because, for example, now I can just write a new export float here, for example, and well, let's call it Toto. And let's just say return 0. That's fine. Here. And now if I do system rescan, now I can displace by Toto. So I didn't have anything to do, I just had to write this simple function code, and everything is reflected. All the rebinding is done internally, but that is something that we really wanted, because if I want to quickly script a new function or change some behavior, it's like, it makes authoring so much faster. If I had to every time recompile some C++, recompile some C#, it will take ages every time I wanted to change something here. I can just say, add these new functions, up, it's available, and it's directly usable. If I, for example, go back, also, yeah, it also picks up in that case. Yeah, Toto doesn't have anything, so let's say return power.
But are you writing a shader, or is this C#?
No, that's shader. Okay. But after it reflects the shader, and there's some C# which well makes the whole binding behind the scene, but it makes it in a generic way, so I don't have to rewrite some C# on top of HLSL all the time. So I just write this function, and as long as it matches the prototype, then it's like we'll make a block out of it. So if, like, for example, I will say export float something like here, test, but I will put float 4 here. Then it will be like, no, I don't know what to do with that because I need this parameter as input. So it's like it's a bit like interface in C# or Java. It's just done at functional level. So you just have to match the exact prototype, and as long as you match the prototype, you just become a node. So that is generally quite useful, because that means I can have a huge library of function of like displays, like operators, have anything we need, like quantize, clamp, absolute, gamma. If I need to make a few new ones, I just write like 10 lines of code and everything is available straight up. So, I mean, when you author and you need to be quite fast for design, it's like really important. And next. So yeah, the only issue is it's very powerful, but sadly, every time Microsoft does something powerful, they tend to deprecate it. So yeah, that's a bit sad because actually you have like a lot of extra, like this library compiler they have a lot of really extremely powerful features, because you can actually really use bytecode to make shader graph as well, but they decided to say, oh, we only want to do vertex on pixel shader. Like, guys, there's something called compute. And so, yeah, we have one unit that scans for the function. You also have still to have it folder-based to not have all the library in one folder. So, like, everything has to be in a specific folder for a specific type. It's just like, well, what you will do normally, but at least I enforce it. And yeah, that's it. On anything, like, for example, if you add anything which is not part of the parameters, like here, they become inputs. So if you see, like, for example, displace planar, you have like any of these parameters, they become parameter, and they're immediately available as well. So that means I can tweak them like straight up, which is also quite nice. So yeah, that's the example that I just shown with code. So yeah, for us it's very simpler. There's a couple of limitations. We had a couple of hacks, but it was not really that bad given the whole advantages. So yeah, as I shown, we can add a new file. We can click rescan. We can, well, I'd like to not only click rescan and have it straight up, but I think it's better. And yeah, well, also, yeah, like FXC is pretty dead. Like, I even spoke to a Microsoft person to fix a bug. They said, fuck you. That was not so nice. Well, not explicitly, but that was pretty much the same meaning. So, well. So now, yeah, the other thing which was really important for us, as I said, like we wanted to work with quads because, well, we had a few hacks. I will explain it very quickly. The thing is, some modifiers are really trivial with quads, and they are extremely hard with triangle. And it's on the bright side also, it's extremely trivial to triangulate a quad. Like you just like have 4 points and you make 3 triangles out of it. It's like 10 lines of compute code. It's like super straightforward. And data structure is pretty similar from triangle. It's just instead of having an int 3 for indices, I have an int 4. Wow, that was 1 character change. That was great. So yeah, triangle face uint4, quad face is uint4. Per vertex data structure, it's exactly the same as triangle because it's just vertices. So we have 0 change. It's pretty awesome. So that means all the vertex pipeline with all the functional things we had, we can reuse it immediately, which is pretty awesome. Predicate points need to be replicated, but that's something I'm working on. A host need to be replicated because obviously a modifier with quad is not the same as a modifier with triangle. So we have to modify only the host, but that means we have to modify 10% of the code base versus like 100%, which is pretty decent. And that's pretty much the same, and pipeline does the same. At the end of the whole passes, we generate a triangle mesh from the quad mesh, and we send it to the pipeline. So we don't need to replicate vertex shader or change code on that. We have exactly the same. Well, obviously, the initial geometric generator need to be duplicated. So because the sphere quad and the sphere triangle is not the same. So that is still something we have to do, for example. Like a rectangle triangle is 2 triangles, a rectangle quad is just a rectangle. So the generators have to be changed, but that's not that bad. So otherwise, so that's how we change the triangle to quad. So we just say this is the index count. So that means now we have the number of triangles is the number of quads multiplied by 2. That was some extremely difficult mathematics. And index count is a triangle by 3. And then here, this is a 2 extremely complex line of code, which say we just take this triangle XYZ and ZXW, and from our quad, we have a triangle. That was, yeah, hardcore mathematics. And so, for example, this type of modifier will be extremely hard with triangle, so I'm going to explain why. Actually, tube works pretty good too, so I think I'm going to take tube instead. So if I take tube here, you can actually immediately see I want to displace my tube with a noise function. But if I'm taking the center of the triangle, that means the center of this triangle is not the same as the center of this triangle. So that means when I apply my noise function, it's a big problem because, well, of course, I want to just have like standard quad. So in some case, that's why I have point selector. But it doesn't work all the time. That's the problem. So I can say it should be diagonal. Here, and I put it on my tube, and it's actually, I did not connect it. Here, and now, so instead of taking the reference point as the center of the triangle, what I will say, I will take a reference point as the center of the diagonal, which is the longest one. So it's a, well, big hack, it works, but it's not ideal, and it works only on the first pass. On the next pass, because I don't have a locality anymore, it's not guaranteed that it's gonna work. Whereas with quad, it's pretty easy because you take the center of the quad, you extrude, you have your quad. So if I do that if I do apply modifier quad here, and I just take a sphere quad here, which is going to look the same normally. Okay, and it should be, I think it's called differently, but that's fine. Yeah, here. And just take my function again. So yeah, the thing is, if I do quad, it just works seamlessly. I don't have to do any hack, which is, so now if I want to say, for example, a window, quad, and I put it here after the extrude, and I need to change, I need to add some whatever here, and now I change the strength. So yeah, it will be the same for this type of thing. So if I wanted to add this little extrusion here, stacking it, like with triangle, at this moment, it will be impossible actually. So I could not even be able to do it, whereas here it's just trivial. So yes?
Do you actually run into situations where you need more than just a triangle or a quad, or can you repeat the question for the screen?
Oh, yes, it was, can you, do you have situation when you need more than triangle or quad? Yes and no. Well, on a technical need, yes. On the fact of having to implement it, it will be quite taking some time. But yeah, I would like to go to higher, like n-gon type of things eventually, but that n-gon really would become extremely more complicated. So that will be a huge amount of work to make it real-time, handle all the edge cases. That will be pretty crazy. So for the moment, well, I would like to do it at some point, but for right now, I still have tons of other things to do.
This window function just adds like 3 quads?
It adds 4 quads and it removes the center one. So it takes 4 quads, 1, 2, 3, 4.
How do you remove? Like it's
I don't remove, I just, because when I do indices, it restarts from 0. So if I don't append the center, it's not here. So I don't really remove, I just don't append. That's it. Well, I will show it a bit. Actually, I can show how it works. Give me a second. I will take a host. I thought I had one, but never mind.
You have about 10 minutes left.
Yeah, no problem. Don't know where I am there. Okay, here. So which one was it? Window. Up. Okay, here. Yeah, so I will. That's how it works. So it will take the face of the quad. It will read the positions. It will read the normal. That's the old indices. So that's what I said with predicate. It will say if you fail this test, you just push back the same quad. Then you apply the displace. Then you check the center. So now I have the center of the position, and I just lerp outside of the position, and I don't re-emit the center. That's it. So I just push 4 more quads. That's done. Okay, so let's see how I am time-wise, because I think. Okay, just checking quickly where I am. Yeah, okay, that's fine for 10 minutes then. Okay, so one thing which was really also important in the pipeline now, which is actually more or less the cornerstone of it, is we have this concept of generation. So that means every phase, every time we create new elements, we append a generation counter to it, which means we can control how we emit. So I will show an example for that. That will be much easier. So for example, here, I can see, okay. So here I did I start with my sphere. Every of these points is generation 0, because it's not, but now when I take my extrude, any of the side will be generation 1, and the top will be generation 2. So now, for example, if I want to do extrude bevel, we'll do that one here. And you see now I'm applying it to everything. And I don't want that, obviously. So now I will have this predicate system, and I will say generation equal, quad in that case. And now I will say, no, I apply it only to generation 1, so that means I will apply it only to the sides, or I apply it to generation 2, which is, well, let's reduce that a little, maybe. Yeah. So now I only apply it to the top. And now, for example, if I want to do an extrude only on those tips again, here, so now you see I already getting a bit overboard on geometry, but it's really low poly scene, so let's do something a bit bigger. Okay. Here. Now if I take this generation equal again, and I say, where was my extrude here? And 3. And let's reduce it a little again. Well, I can just do clamp, that will do. Clamp. Here. So now I only apply it to the tips. So you can start to create really complicated structures by just controlling. So it has, well, big advantage. There's a lot of control. It's like emits much less geometry because it's done as predicates, and you can quite do well, obviously, plenty of animations on top. But that is the most important part of the pipeline. Like, this is what allows to create all this geometry, to say, I want to apply it here, only here. It's really, well, it will take more than 10 minutes to explain, so, yeah. But yeah, that's basically, well, the slide is basically what I said, but explaining it on the, so I will skip that one. Well, okay. And so there's still a bit of control. So we can say, for example, if you fail, if you have a 0 displace, you fail the test. So we have a bit of control to just like save emitted geometry, because if you have a 0 displace, you still push the same triangle. So there's no point of like emitting new geometry for something that looks exactly the same. Well, in some cases it does, but in most cases it doesn't. But it's controllable, so you can say if I don't need it, I save performance and geometry so I can do more. If I really need it, I can do it. So yeah, only still issues right now, but it's like, yeah, determinism is the next part I'm gonna work on, because the idea for now, displace function works with a position, not with ID, because IDs are not guaranteed in GPU. So like, for example, you emit a new vertex, it can be 35 one frame, next frame it can be 37, you don't know. And that's a huge issue, because, for example, if you want to do a hash function on the ID, it's impossible, because every frame you're gonna have a different hash. So it's not gonna work. Well, massive flickering. Without predicate, it's easy, because actually you would not even need to use atomic, so you can just use simple math. But in our case, we need this. So, and yeah, problem with position-based calculation is if you change something in one pass, it impacts the next pass, because the position moves. So if I, for example, I think I can fit that in the next 5 minutes. Yeah. So let's say, for example, I will take a noise function. Okay, here. You do it on the extrude, here. And now I will do the same here, actually. Okay, so now the problem is now, because the position change, you can see this displace will impact this displace, because when I'm gonna move this point, the reference point on the next stage is gonna be different. So that is quite the problem. Yeah, and so so for future works, there's because obviously I'm not done with that type of things, I'm gonna continue to work on that pipeline. So generation tests for now are predicate. I want to make them common, because for now I have to replicate them. Also, that will allow to write more custom predicates to split them. And next part is also, the next part is to get fixed ID no matter if you do primitives. And I found a very stupid technique which seems to work. So I will try to explore that stupid technique, which is to use virtual ID for vertex. But that's something, well, maybe you'll see it on next talk then. Okay, so if you have questions around, well, I'm still, okay, probably a lot, but yeah. Thank you. Yeah, it's very hard to condense all this in 1 hour. But I hope it gives you idea on concept, how it works. I hope it was beneficial. So questions? Sorry? Mesh shader, you mean? On mesh works more at pipeline level, so it is good at draw level, but for generation I will still need to use compute, and mesh shader is DX12 only, and my pipeline is still 11. So I did try them on some custom things, but yeah, it will take a lot of time to integrate. Yes?
You talk a lot about conditionally generating geometry.
Yeah.
What about simplifying or removing them?
That has, well, you have some cases which are trivial. Like, for example, you want to say, because you can say, like, for example, if you don't want this triangle, don't emit it. So that type of removing is not that hard. Simplifying is a complete different topic. Like simplify, but in my case is more to start from simple primitive and make complex one, not the other way. So it's not something that will benefit my pipeline that much. And it's really hard to do in compute as well.
So in the first pass, you calculate the vertex data and indices, and then you convert to triangles, and then you calculate normals?
Yeah, for normals, because I have indices, I have one compute pass which gets all the triangles that this vertex belongs to. Then I sum the area of all the triangle and I divide by the weight, and so you can recompute normals because you can access neighbors as well. So yeah.
It's like a different pass.
Yeah, it's a pass I do at the end normally. Yeah.
So you have like 3 passes in total?
For that, it's 2. Okay. There's like 1 to calculate adjacencies, and then 1 pass to compute normals. Yes. Any other question? Or? Yes.
How do you deal with different materials on a mesh?
For that, well, UV is a huge problem, obviously, with that type of geometry. So, well, most of the time, I admit triplanar is pretty nice. It does a good job. So, yeah, triplanar. In some cases, I can reproject UV as well, but most of the time, triplanar is, for this type of things, I mean, you can't really redo a UV map on draw, plus I want to animate that thing every frame, so that will make no sense.
More like referring to, let's say you have a sphere, and then you might have a modifier that like colors the sphere faces with different random colors or something, and then keeps these colors for the extrusions.
If I extrude, yeah, I can, for example, if I have the color, I can keep the color on the emitted. For UV, I can say take the center, but it's not always going to look good, that's the problem.
Can you like have modifiers that put some attributes, extra attributes in there that
Yeah.
you can reuse?
Yes, like they can write object IDs, they can write object center, they can rewrite colors, they can modify UV. So yeah, there's quite a bunch, yes.
And then you can also like say like split the mesh into different meshes by the attributes or something?
Not by attribute, by other things, yes. I use generation for that, so I just say, I don't really split the mesh. I say, if you're in this condition, you become this gen. If you become this, you become this gen. So it allows some funny effects like splitting plane, and you can say, for example, this side of the plane you extrude pyramids, this side of the plane you extrude tubes, for example. So yeah, I technically split by generation, yes, in a way. Okay, so thanks for attending.